maxima and minima of functions of two variables. Okay. A function of two variables that's going to be too hard to catch up on. Let me try again. Two variables has a local maximum, so like the top of a hill. So a function of two variables, if you were going to depict it in a picture, would be a surface, okay? Because you're plugging in. Yes? Yeah, quite right. This light's too bright. There we go. Thank you. So a function of two variables means that the domain is two variables, x and y, and your output is single variable, z, and so you can draw it like a surface. So by a maximum here, you can picture it like the top of a hill. And a minimum, you can picture it as like the bottom of a valley. Okay? So a function of two variables has a local maximum at some point in the domain AB if, what does it mean for it to be a maximum? It means that all the function values nearby will be smaller. Okay? That's what it means to be a maximum. When xy is near AB, where near is a rather ill-defined sort of word. If we were wanting to be exact, we'd say something like for xy element of an open region containing AB. But we'll just use near. So this is local max and local min that we're looking at here. Absolute max and min is a bit trickier, and I'll get to it at the end of today's lecture. And then basically that same sentence again, only with minimum and the inequality the other way around. A function of two variables has a local minimum at AB, please keep quiet, if all the function values are greater than f of AB, when xy, please keep quiet, is near AB. Okay, so that's just basically, that's not just breaking news here, that's essentially the definition of a maximum. How do you find it? If f is differentiable, now let's think about how we find turning points in single variable functions. We say, okay, if you draw a squiggly curve and we want to find a turning point, we want to find a maximum or minimum, what we realize is that the tangent line at a turning point is horizontal. And so so the way we find turning points is by looking for where our tangent line is horizontal, so where our derivative is 0. Now, of course, that's not foolproof, because sometimes it'll find saddle point type things like this, inflection points like that, where we do actually have a 0 tangent, but it's not actually a max or a min, but it's certainly a good start. To try and find where our derivative is 0. And we're going to be doing something very similar in two variable functions by recognizing that if we have the top of a hill and we slice through it with a vertical plane, the curve of intersection of that surface and the plane is a curve that has a maximum just like in first year. And so any tangent line to that curve at that turning point at the top of the hill would have a slope of 0. Now, of course, there are infinitely many vertical planes that you could slice this top of the hill with, but we look at two in particular. We look at the two that are parallel to the xz plane and the yz plane, where our tangents have the slopes of the x derivative and the y derivative. So what we're going to look at particularly is where is the x derivative 0, where is the y derivative 0, and we're looking for the points on the surface where both of those derivatives are 0. Again, it's not foolproof. We can sometimes find points where the x derivative and the y derivative are both 0, but it's not actually a turning point. And the way we check that is with a second derivative test, just like we can in single variable calculus. Okay, so a lot of chit-chat, let's write that down. If f is differentiable at AB and has a local max or min at this point in the domain AB, then every curve of intersection Yeah?
First line of the second paragraph, we wrote at the end of the first line of the second paragraph. We wrote
I wrote AB, but my stylist decided not to. Thank you for pointing that out. I didn't notice. Behave. In every curve of intersection of where am I? Of our bumpy surface that we're trying to find the max and min of, with a vertical plane, catch up with me, stylus? I just wrote the word through. Hello? Through AB will have a local max min. So we're looking for the maximum and minimum of a surface, but we find it by understanding how we find that maximum or minimum by understanding the process of finding the max min of a curve. So we have that our x derivative at AB is going to be 0, and our y derivative at AB is also going to be equal to 0. And in fact, all our directional derivatives, in fact, should be 0. But we're going to look at these two special cases. So the summary of all of those is that grad f at AB, sorry, I wrote xy, I'm meaning AB, is equal to the 0 vector. Okay, the stationary points of f are points where grad f is equal to 0. And then we need to decide, is it a max, is it a min, or is it in fact neither, and it's actually just a sort of a false positive in a sense. We then need to decide if these stationary points are local max, local min, or neither. Okay, and so we do the second derivative test, which I'm going to give to you without a derivation. You will find this in your textbook, but I have a little warning, and I've put that warning into a box in my handbook, and I left my handbook on my desk. But there's a box on page something or other, 70 something, and it gives the stuff that I'm busy writing down now, but it also gives a little bit of a warning. What page number is that, somebody? 74, thank you. The second derivative test looks like this. Let big D equal the determinant of this matrix, which looks like a derivative, well, it is a derivative matrix, but it's a matrix of the second derivatives. Okay, so if we work that out, it'll be fxx times fyy minus fxy squared. And then we evaluate that at this point, that the stationary point we've managed to find, evaluated at at AB. Okay, and then there's this, if D is greater than 0, then we do have a maximum or minimum. Okay, so D greater than 0 means yes. D smaller than 0 means no. Okay, but we need more than just yes. Yes, we have a max or a min, but which one? And here I find this fairly easy to remember because this matches with our single variable stuff. Remember that in single variable calculus, if the second derivative is positive, it means our function is concave up, like a bowl, and it must mean that the turning point that we found is a minimum. If our second derivative is negative, it means our function is concave down, like a dome of a roof, and it must mean that the stationary point we found is a maximum, and this matches. Okay, so if our xx derivative is greater than 0, then what we found is a minimum. Then f of AB is a local min. D greater than 0, still thumbs up, but now what if our fxx is negative, we have a dome shape, then this is a local max. If D is less than 0, it means we do not have a maximum or a minimum. We probably have a saddle point. Then f of AB is neither max nor min. Saddle point. Oh, excuse me, I'm going to sneeze. Oh, excuse me. Oh, excuse me, I apologize. Because basically we've sliced it one way and we've seen a minimum, and we've sliced it the other way and we've seen a maximum. Even that is not necessarily true. So I'm just going to write here possibly saddle point. But basically it's neither. It's not a max or a min. It was a false positive. It's not what we're looking for. If D is equal to 0, then that's not a nice result to get. It basically means it could be a max or a min, or neither. We don't actually know. We need to do further investigation. The stuff we've done so far is not good enough. We need more. We need more information. Chances are it's not a max or a min, but we can't be sure. We need to do something different. And for this thing over here, a good technique for this more information is to slice through our surface with some quite carefully chosen surface. And you can be quite strategic about this by looking at the formula for your surface and thinking, wouldn't it be nice if that term disappeared, or if we were able to add those two terms together, and you choose your intersecting surface quite strategically. It's to slice through this with a chosen surface. To see if we get basically that sort of shape or a contradiction. Like some of the information is telling us we have a max, and some of our information is telling us that we have a min, in which case we've got some sort of saddle point and we know that we can move on. And that's it really. Okay, so that warning in that box. When I first started teaching this course, Alan Reinhardt gave me his notes. Alan Reinhardt is a giant of this course. He's been teaching it for many, many years. And he gave me his notes to work from, which was extremely useful. And in this particular section, the way that he derived the second derivative test is he used something that was very similar to your quadratic root formula, where you have your discriminant, that b squared minus 4ac thing that you have under the square root. And the big D that he ends up with, and you probably find is also in some textbook somewhere, but not in our textbook, actually has those two terms the other way round, because it bears that resemblance to the discriminant. It actually has the fxy squared first minus the fxx/fyy. So if you were going to set it up as a determinant of a matrix, you'd actually you'd swap your columns. What that means, and then of course you would actually interpret, then D negative would mean that you have a turning point, and D positive would mean that you didn't. So what I'm saying here is that if you look at old resources for this course, old tests with the written up solutions, or maybe, I don't know, I must admit I'm not sure what second derivative test the other two lecturers for mainstream are using. It's possible that in other resources for the same course you might find the second derivative test constructed differently. In which case the conclusions reached will still be the same, but the process of getting there will be different. All the signs will be the opposite of what you're expecting. So when I started teaching this course, I then had a choice, because should I go with what the textbook has, or should I go with what the notes that I'd been given, which are obviously quite entrenched historic notes for this course, and I decided to go with what the textbook is doing, so that when you go and do some textbook homework, the second derivative test that I've been talking about is the same as what the textbook is talking about. But I just want to warn you, if you look at other people's notes, maybe even today, but certainly ones from the past, and this course hasn't really changed in the last 20 years, literally, the last 20 years, probably longer actually, you might find a slightly differently constructed second derivative test. So I just want to give you that warning. Okay, all right. But obviously the conclusions reached about maximum will be the same, but you'll just see slightly different stuff to do with signs. Okay, let's jump into an example. I am going to do, I don't have my handbook, but I do have the solution, so that should be fine. I was going to do 7 and 8 and then ask you to do 9 and 10. But 8 is quite long, and 10 does the same thing, only faster. So I'm going to do 7 and 10, and then I'm going to invite you to do 9 and 11. I will put the solutions for 8 up on Vula, but we're quite pushed for time, and I'd rather not do a really long problem. So let me demonstrate with number 7. Okay, we've got this function f of xy equals x cubed plus y cubed minus 6xy. Okay, so we want to find the local maxima and minima of that function. So I'm going to solve for my x derivative and set it equal to 0, and my y derivative and set it equal to 0. So my x derivative is 3x squared minus 6y, and I'm going to set it equal to 0, and I'm going to call it equation 1. And my y derivative is 3y squared minus 6x, and I'm going to set it equal to 0, and I'm going to call it equation 2. And now I have two simultaneous equations in two unknowns, and I'm going to solve for x and y. Let's have a look. What am I going to do here? I'm going to take equation 1, and I'm going to make y the subject. 6y equals 3x squared, which implies that y is 1/2 x squared. Okay, and then I'm going to substitute that into equation 2. I am at the bottom of my page here. 3y squared, so it's 3/2 x squared minus 6x equals 0. I'm going to do a page jump. There we go. What have I got there? I've got, that'll be a quarter, so it'll be 3/4 to the 4 minus 6x equals 0. I'm going to take x out as a common factor. And I get x equals 0, or 3/4 cubed equals 6. In other words, x cubed equals 6 times 4/3, so that's 2 times 4, that's 8, and x equals 2. So I've got two solutions. And my relationship of y to x was that y was 1/2 x squared. So that's going to give me y also equals 0, and that's going to give me y equals 1/2 2 squared, which is 2. So I have two stationary points. Zero, 0, and 2, 2. Let me show you a classic error. A classic error, and I think really in the true sense of classic, it's timeless. You'll probably find people making this error back in the time of the Babylonians. Classic error, okay, is to divide by x on both sides. Okay? Okay, if you divide by x on both sides, you're just left with 3/4 x cubed minus 6 equals 0, and then you would solve it and you would just end up with the one solution. Because dividing by x, you are slamming the door shut on the option that x could ever be 0, because of course you can't divide by 0. So be very careful in this, and also in Lagrange multipliers, which you also end up having to solve simultaneous equations. Beware of dividing through by an unknown. If you divide through by an unknown, you are saying this unknown can never be 0. And maybe you have good reason to know that it can never be 0, in which case it's fine. But if you're not sure, then don't divide through, rather take it out as a common factor. So there you go, classic error. Your phone isn't going to write your exam for you. Okay, now we need to do the second derivative test. So let's have a look. I'm going to need my 4, but 2 of them are the same. My 3 second derivatives. Okay, I've scrolled past. Okay, I'm going to differentiate my x derivative with respect to x. And for this one, I can either take my x derivative and differentiate with respect to y, or my y derivative and differentiate with respect to x. Either way, I should end up with the same result. If I don't, I've made a mistake. And then my y derivative is 6y. Okay. So I'm going to... Now, there's a variety of ways of writing this. I'm going to evaluate d at the point 0, 0. I know I write this differently to the way some other people do, but I write it the way that makes sense to me. So if I do a little crisscross determinant, it's 0, subtract 36, negative 36. Okay, that's smaller than 0, 0, 0. And I like to add in the z component of the z coordinate as well. If I plug x equals 0 and y equals 0 into my function, z is also 0. Neither max nor min. And then if I work out my d at 2, 2, I've got 12 minus 6 minus 6, 12. That's 144 minus 36, which you can work out, but it's enough to know that it's greater than 0. Also, our x derivative was also greater than 0, so we have a local min. So 2, 2, let's plug x equals 2, y equals 2 into our function. According to my notes, we end up with minus 8, is a local minimum.
Sorry.
Yes.
So you plug the...
I plugged the x equals 2 and y equals 2 into my original function. If you don't do that, it's all right. But I like to do it. I like to get the actual point on the surface rather than just the point in the domain. But just the point in the domain is good enough. Question?
Can you explain it without the decision not say whether it's a maximum or...
Okay, it's the second derivative test, and the second derivative test, d is greater than 0. Actually, let me put that in black. D is greater than 0, which means we do have either max or min, and our x derivative, which is this thing here, is greater than 0, which means that you can think of it as concave up, so we have a min. Second derivative positive, concave up. Second derivative negative, concave down.
Can you explain for the first one?
Negative, it means that, it kind of means that there's a disagreement. That negative, you're going to get a negative determinant to that if your second derivatives essentially disagree about what's going on. So that's how you end up getting a negative. So what's happening there is I'm not sure what this looks like, but it'll be the two-dimensional, it'll probably be a 3D, a surface equivalent of something like that. So it'll be a surface equivalent of this. Okay, where it looked temporarily as if there was in fact there is a stationary point, but it's neither max nor min. It could also be like a saddle point, where that point over there is a maximum from one point of view, but it's a minimum from another point of view. I'd have to do some more investigation to figure out exactly what's going on, but fundamentally what's happening there is there's a disagreement. My second derivatives are coming in with a little bit more descriptive power than my first derivatives, and I was saying, sure, that's what the first derivative said, but there's disagreement here. There's something funny going on. There's no actual turning point. Question?
Can you just get a minimum and that's fine? You don't have to get both.
Correct, yeah. Well, if you think about a paraboloid only has a minimum, it doesn't have a max. Local, yeah. Okay, all right. So it's really very mechanical. You work out your derivatives, you set them equal to 0, simultaneous equations, boom, you're back in high school. Solve your simultaneous equations, and being careful not to lose any solutions along the way by dividing by unknowns. You end up with a list of stationary points. Then you work out your second derivatives and you do your second derivative test for each of those stationary points. And you're done. Finished. It's incredibly mechanical. Sure, compare this to like Stokes' theorem. Flux problems. You better, if you get something like this in the exams, it's very nice. Okay. In 2015, it was this. Was it this? Or was it Lagrange multipliers? I think it was this that we did right at the end of the semester, and it was right when the 2015 protest started. So some people were present for the lecture and some people weren't. It was that 19th of October. And it was all put up online, but the word came down from the head of the maths department that anything that was covered on that day couldn't be included in the exam. And we had included one of these in the exam already, and it's so easy. And we didn't want to take it out because it was easy marks, and it would make the exam harder for us to take this out of the exam. So we put in a question choice. With this and I think a Newton or an affine or something. Anyway, so if you go and look at the 2015 S exam, you'll find a question choice, which is very unusual. You don't usually get this. But it's because we really agonized over taking this question out of the exam because it was actually so easy. But at the same time, if people were actually involved in the protest, they will have missed the lecture, this whole thing. Anyway, so that explains the question choice in 2015. Okay, question 8 is one where one of the second derivatives tests gives us 0. But it's quite long and involved, and it's a nice one, but we're pushed for time. So I'm rather just put that up on Vula, and I'll do exercise 10, which also has a d equals 0, but it's a little bit faster to do. So here we go. F of xy equals x cubed plus xy squared. The x derivative, let's have a look at the x derivative. It's 3x squared plus y squared. And the y derivative is 2xy. Make them both equal to 0, 1, 2. That second one equaling 0 means that either x equals 0 or y equals 0. 2 implies that x equals 0 or y equals 0. Those are the only possible solutions. If x and y are both non-zero, then 2xy will not equal 0. So basically, I've already solved my problem. I just need to figure out. So if I plug x equals 0 into equation 1, I'll get 0 plus y squared equals 0. That must mean y equals 0. If I plug y equals 0 into equation 1, I'll get 3x squared plus 0 equals 0. That means x equals 0. Looks like I only have one solution. 0, 0 is the only stationary point. Okay, cool. Let's do the second derivative test. My xx derivative is 6x. My xy derivative, which is the same as my yx derivative, is 2y. And my yy derivative is 2x. So you can see what's going to happen here. When I plug in my point, I'm going to get 0, 0, 0, 0. And you work out that determinant, and it's 0. So we need more information. So how are we going to get more information? Need more info. Okay, so for this, what you do is you go back and you look at your original. It's much easier to prove that we don't have a maximum than it is to prove that we do. So you cross your fingers and you hope that this thing actually is a false positive, that in fact our function doesn't have a local maximum at this point. You cross your fingers and hope that's the case, because that will be an easier thing to find. So you, went too far. So you go back and you look at your original function equation and you think, how can I break that? What can I intersect that surface with to leave me with something where I go, oh yeah, okay, it's obvious I don't have a max or a min. And in this case, I would say we want to intersect it with the vertical plane y equals 0. Why? Because my first term is a cubic. My second term, well, I suppose my second term is kind of a mixed cubic because it's x to the 1 y squared. But my first term is a nice, clean x cubed. I know what the graph of z equals x cubed looks like, and I know it doesn't have a max or a min. So very strategically, I'm right at the bottom of my page here. I have to do a page jump. Curve of intersection of the original function and y equals 0 is z equals x cubed. So we choose that very strategically. Chosen very strategically. I suppose another good choice would be to intersect with y equals x. Y equals x would achieve similar result. Because then we'd have z equals x cubed plus x cubed, and then we'd still have a cubic. Z equals x cubed. Because the thing to remember here is that if we truly do have a local maximum, the top of a hill, it doesn't matter how we slice it, our curve of intersection will have a maximum. If you have an actual top of a hill, you can slice it any way you want. You can slice it with planes, you can slice it with parabolic sheets, you can slice it with all sorts of funny things. If it truly is the top of a hill, it can't look like anything other than that. Every curve of intersection will have a maximum. You can't truly have the top of a hill and then slice it and suddenly have something that doesn't have a maximum anymore. It's geometrically impossible. Question at the back?
Now, do you slice it with a plane which is vertical to the two variables in the function? So like it's f of x, y, so you have to slice it with a plane which is...
I'd recommend slicing it with something vertical. Yes, slice it with something vertical, so it'll be some equation that only has x's and y's in it and doesn't have a z in it, so that you can think of it as a curve on the xy plane that you're then pulling out to make some sort of vertical surface. Planes are the easiest, but in fact the one that I was going to do, exercise 8, I think we went for a parabolic sheet. What did I intersect it with? Yes. I'll put it up on Vula and you can check it out. Has no local max nor min, so neither does f of x, y. We sliced it in such a way that when we looked at the curve of intersection, we saw something that looks like this. That is an impossible curve to see if your turning point, if your stationary point, I beg your pardon, truly was the top of a hill or the bottom of a valley. You could not get that. It's geometrically impossible. Okay, you give it a go. Try number 9 and number 11. Number 9 is a straightforward one to interpret, and number 11 is another one of these ones that has a d equals 0. And just so that you can check yourself, in number 9 you should find 4 stationary points, which you can then interpret. And in number 11 you find 2 stationary points, one of which is one of these inconclusive ones. Okay, so you give that a go.